Hey everybody, today we're going to talk about the structure of the atom and a little bit of the behind the scenes of the history of how we came to this idea of the structure of the atom. So when we're talking about the structure of the atom, I know that there are things that you have learned before, like for instance, the electrons live in the electron cloud and they are negative. They are negative, and the protons and the neutrons live in the nucleus, and the protons are positive, and the neutrons do not have a charge. Those are things that you already know. You know that the nucleus is dense and that it's in the center. Those are all some things that you already know. Pause this video right now and write those things down so that you can remember, aha, I know that. All right. So in our whole process here, I have decided that we need something to help us keep track of all this vocabulary we need to be able to use. And that's going to be called a personal word wall. You're going to find this in your modules, but I wanted to take a moment and take a look at what does that thing actually look like. So you're going to go open your personal word wall for Unit 3, and this is exactly what this looks like. This is nothing more than a worksheet, but it is meant for you to add this to your notes. And the way you're going to use it is for each and every one of these terms, you have a picture. And you may know it right now. You may not know these terms right now. And so right now, what I would like you to do is stop the video, stop within class if you're in class, and I want you to go find in your modules this personal word wall. I want you to make a copy into your folder for chemistry, and I want you to fill it out. And the way I want you to fill it out is I want you to actually go in and measure, not measure, but let's use the terminology of label it. Let's say if I did not know a term, I would write down X. I don't know it. If I did know it, if I did know the term, I would mark it as an X, and then I would go ahead and type in myself a sentence that explains what that term is. And by sentence, I truly do mean that you're going to use capitals and you're going to use periods. You should have a sentence that tells you what that word means in your own words, because this is not going to help you by copying and pasting from the internet, though you're welcome to look those things up if you feel like you just need some help. But what I'm trying to tell you is that you are going to want to use your own words, because this makes this document more valuable to you if you have taken the time to put this stuff into your own words. Okay, so that is enough about, well, how does a personal word wall work? I'm going to ask that you turn this in on the last day of this particular unit. It will be a formative grade. Until that time, you are responsible for this document all by yourself. You can fill it in as we go along. You'll probably be able to fill in a lot of these as we go through this particular part of this presentation today. Okay, so let's move this along here, and let's go ahead, and I'm going to close our personal word wall, and we're going to go back to our next part of our presentation. So take the time right now to press stop. And what I would like to do is ask you, what are the charges of the subatomic particles? This should be review. So stop the video and please go ahead and answer the question. Okay, so by now you should have had time to answer the question. And what we're going to go do is each one of these, we're going to use a process of elimination to decide which one is the correct answer here. So what are the charges of the subatomic particles? That is what we are looking for right there. What are the charges of the subatomic particles? We need to make sure that we know what is meant by that term subatomic particle. Something must be going on there. Sub means under or inside, like a submarine is under the ocean. So subatomic means inside the atoms. This means that what particles do we know that are inside the atom, and it's asking what charges are those. So I get to be able to cross out, I'm going to change my colors here. I'm going to cross out the first one because it says protons are negative, and I know that's not true. And I'm going to go look at the second one, and I've got protons are positive. Yay, that's correct. But I'm going to cross out neutrons are positive because I know that's not true. Neutrons are neutral. And then I'm going to go on to C. See me using the process of elimination. Then I'm going to go to C, and it says protons are neutral. And I'm going to cross that one out because I know that's not true as well. That leaves me with only one answer left, and that is my correct answer. Did you get the correct answer? I hope so, because that information should be review information. All right, so the first thing we're going to do is start talking about a little bit of the historical ideas of what types of atomic models we had. The first one is by a scientist called John Dalton. He viewed the atom as a small solid sphere. He thought that the atom was the smallest particle there could be. He said that atoms of the same element were the same as each other. That part is true. He was not right about an atom being the smallest particle of matter. He was not right about that because now we know about protons, neutrons, and electrons. What he also didn't know is that some atoms of the same element can be different from each other, and we are going to learn about what makes them different from each other. And when atoms of the same element are different from each other, they are called isotopes, and we're going to learn about isotopes in this unit as well. He also came up with the idea of this law of multiple proportions. That means that he said that different compounds could combine elements in different proportions. And usually the same compounds always had the same proportional difference between their atoms. So in other words, water is always 2 hydrogens to 1 oxygen as its proportional ratio of its atoms. All right. So then we go on to J.J. Thompson. And if I haven't said it already, you should be in your notes making note of who these scientists are. You have already heard about J.J. Thompson in our notes that we took from the last class period, but here he is again. Ooh, you guys, that must mean that he needs to be noted down. And so let's take a note of what he did. He said that the atom was like a plum pudding. And in a plum pudding, there is the bread part of things, and there is the raisin or plum part of things. And he said that the plums were where the negative charges were, and that the rest of the bread of this English pudding was actually the positively charged background. And as you know already, that's not exactly right. That's not exactly what we believe today. He said the electrons were randomly arranged, and we sort of think that, but he said the positive was spread out across the atom, and we know that's not true today because we know about the nucleus. He used the cathode ray experiment to prove the existence of negative particles because of a deflection he saw in the stream of electrons when an electric field is added. So when the electric field was added, he was able to say, look at it being deflected towards the positive side. And from that, he made the connection. What is attracted to positive? He made the connection that negative things, negative particles, were attracted to the positive side of the electric field inside this cathode tube. All right, these are things you should all have written down in your notes. All right, our next scientist that we need to talk about, it was also mentioned in the previous video you watched, is called Ernest Rutherford. He used something called the gold foil experiment to figure out that there was a small, densely packed area in the atom where there was a positive charge. And here's what happened. He used a source of power called an alpha particle emitter. An alpha particle is really 2 protons and 2 neutrons. And so we have an alpha particle emitter, and it was shot. It is, by the way, an alpha particle is positively charged. So it was shot through a very, very thin piece of gold foil towards a a piece of negative photographic negative material that was called the detecting screen. And what he expected to see is that his charged particles would pass right through the very, very thin gold foil. You might ask, well, how thin was that? Well, it's about 6 atoms thick, so it was really, really thin. And so he shot it through there, and he got pretty much exactly what he expected, except do you guys see those 2 arrows that are going back in the opposite direction? Those 2 arrows were the problem and turned out to be the basis for what he said was going on inside the atom. So he said that there must be something inside the atom that is repelling these positively charged particles I'm shooting through here. And so the only thing he knew of that would repel positive was another positive. So that's where he came up with the idea that because very few of these particles were shot back in the opposite direction, the nucleus is small. It must be densely packed, it must be positively charged, and the rest of the atom is simply empty space. I cannot be clearer about this. You need this information in your notes. You need to know the gold foil experiment, and you need to know what he found. That is by far the most important part of this. Okay, so we are going to move on next to our next question. We are talking about Niels Bohr now, and you have learned about Niels Bohr before because you've learned about the Bohr model. And in the Bohr model, Niels Bohr proposed that electrons traveled in specific circular orbits. Now, do you notice that he's not talking about protons? That's because Niels Bohr and Ernest Rutherford were scientists who worked alongside each other at approximately the same time. They were slightly of different generations, but they worked in the same circles of scientists, if you will. And so they were doing complementary work. They were not trying to so much compete with each other, even though scientists really do like to compete with each other. So Niels Bohr said, well, here's the electrons. He said the electrons are found outside the nucleus. They orbit, in fact, like planets orbit the sun. So he called this the planetary model. You need to make sure that you know that this is called the planetary model because electrons orbit like planets, or orbit the nucleus like planets orbit the sun. Okay. All right, so here's our next question. Which scientist proposed the view of the atom as an indivisible, in other words, undividable particle? And I strongly recommend you stop and you pause it here and you try to figure this out. Okay, so hopefully you've paused and you've tried to get the answer here. But let's go back and make sure that we can remember what each of these scientists did so far so that we can use a process of elimination. Thompson said there were negative particles inside the atom called electrons. Okay, so he said there were negative particles. Dalton said the atom was really just like a sphere. He said the atom was like the smallest particle of an element. That atom was the indivisible particle. Bohr said that the atom has a nucleus and then the electrons that orbit the nucleus. That's what Bohr said. And Rutherford got credit for identifying the positively charged nucleus. All right. He didn't actually know that there were protons and neutrons in there. He just said there was a positively charged particle. So if you chose Dalton as the correct answer here, then you got that one right. Okay, we're going to move ourselves along here. How about this one? Which scientist determined that the atom is mostly empty space? Let's remember again that Thompson said there were electrons. Dalton said the atom is the smallest particle. He was wrong, by the way. Bohr said that electrons orbit the nucleus like planets. And we said Rutherford identified the positive nucleus, but he also said that the rest of the atom was almost entirely empty space. There's a little bit right and a little bit wrong about that. But the one who said the atom is mostly empty space is Rutherford. Okay, hope you got that one right. All right, let's take a look next. How about this one? How did Rutherford prove that there was a positive nucleus? All right, hopefully you've been able to figure this one out. Let's make sure that we can also figure this one out. All right, so the cathode ray tube, that was Thompson. So not Rutherford. He used a stationary model to hypothesize the nucleus was positive. Is that what the model was called, stationary? Or is it better put that he used a gold foil experiment? I think that was the correct answer. The single indivisible particle, that was Dalton. All right, did you get the right answer? I hope so. Okay, we're going to move ourselves along. All right, part of your notes that you have already written down is protons are positively charged. You have also written down that they are found in the nucleus. It is time for you to add that they are 1,837 times heavier than the electron, which is why we often say that protons and neutrons make up the mass of the of the atom, and that electrons have a very negligible mass. So small, in other words, that they don't count towards the mass. All right, so you should have added by now that protons are 1,837 times heavier than electrons. Okay, now, so let's go ahead and also add to our notes that protons are found by looking at the periodic table and looking at the atomic number. So when we are looking at the atomic number, we are literally talking about that whole number that is found on the periodic table. Sometimes it's in the upper left, sometimes it's in the upper right, sometimes, as in this one, it's right above the symbol for the element. This helps us differentiate different atoms. Every atom of every element will have, every element will have a different number of protons. Every atom of that element will always have the same number of protons. Will always be a whole number. Okay, got out of this, but we're going to pause. Okay, we were not at the end of our slides. So you can also see some of the other placements of the atomic numbers here, with nitrogen being 7, and you can notice that that is in the upper right hand corner, and calcium being 20. And we are always going to have to look up elements on the periodic table based on their atomic number. All right, so how many protons does magnesium have? It is time for you to stop right now and go back to your modules and locate the chemistry reference materials. This is going to be the place you find your periodic table. So go ahead and stop right now and go locate that information. Okay, so this literally means that you need to go back to your module and go find your chemistry reference material. And here it is. Here's my chemistry reference material. And we are going to go take a look at what this has in it. This has all kinds of equations, as you can see, as we're looking through here. But you will also notice a periodic table. And so this is going to be a periodic table for you to look at as you are looking for the answers here. And so let's go see if we can find magnesium. And when we go hunt and hunt and hunt and look, we are going to find magnesium right here. And so magnesium, as you can see, has the number 12 over the top of it. That must mean that's our atomic number. So we are going to go navigate back to our presentation, and let's go see if we can answer, how many protons does magnesium have? Hopefully you have picked by now the number 12. Now, that is our correct answer, but let's see if we can go see what else is on here and see if, well, what are we looking for here? So let's take a moment, and I'm going to erase and get my mouse back, and I'm going to go back to those reference materials. What other number on magnesium was also on that list? Does everybody see, for instance, this little number down here on the bottom? Well, that one is the atomic mass, and that is actually magnesium's atomic mass, but it is not the atomic number, which is equal to the protons. That is a different number, and it is always going to have decimals that follow. So this one would not be correct. If we said 24, we would have been talking about chromium. There were two other numbers on our list. If we had picked number 6, we would have been talking about carbon. And if we had picked number 7, we would have been talking about nitrogen. So literally, our number of protons literally has to do with the atomic number, and it changes the atom if we change our number of protons. Okay, let's go on back to our our presentation. So how many protons? We said that was 12. Okay, how many protons does calcium have? So here we go. We're going to run back to calcium, and we're going to go look at calcium. And if you take a look with me here, calcium is right here. And you'll notice that calcium has the number 20 over the top of it. So calcium must have 20 protons. So we can go back and say, haha, the answer here is D for the number of protons does calcium have. All right, we are going to finish up with electrons and neutrons, and then we're going to stop our presentation. So here we go. You have already written down that electrons are negatively charged, and you already know that they are very lightweight. In other words, they are very, very small, a very, very small part of a proton, and they are found outside of the nucleus in the thing that we call the electron cloud. All right. So even though they are lighter than a proton, they have the same sort of charge except in the negative direction. So while protons are positive, electrons have the same magnitude of charge, just negative. Be sure you get that part written down as well. So for those of you going, what should I write down? You should have down that they have a negative charge and that they're found outside of the nucleus in the electron cloud. And you should be writing these things down. These are all things that are part of your notes. And I cannot explain to you enough how much you need to be writing notes. And I know you know this. All right, let's continue on. More about atoms. Okay, so we have atoms that contain the same number of protons and electrons. And when we use that terminology, we mean that they are neutral. In other words, neutral atoms, or just even saying the word atom, by saying the word atom, we mean protons equal electrons. We want everybody to know that when we say the word atom, so in your notes, you should say an atom has an equal number of protons and electrons. It is literally called something else if it has a different number of protons and electrons. And we will talk about that, don't you worry. Okay, we are on to the neutron. As you know, the neutron is also located in the nucleus. You should add to your notes that a gentleman named Chadwick is given the responsibility or credit for having discovered this subatomic particle. Okay, he determined that neutrons have the same mass as a proton. You should add this to your notes. Neutrons have the same mass as a proton. They are found in the nucleus. They have no charge, and they are considered, for that reason, neutrons are neutral. So that should be obvious. Everybody should be going, oh, okay. This combination of subatomic particles are what's considered our modern atomic theory. In other words, protons and neutrons are located in the nucleus. Protons are positive, neutrons are neutral. Electrons are also subatomic particles, but they are found outside the nucleus in the electron cloud, and they are negative. You need to make sure that you can talk about the modern atomic theory